Welcome back to another amazing episode of the Drew Sutton Leadership Show. Today we're talking with revolutionary power innovator Anatoli Oleynik. Anatoli is a pioneering innovator transforming the global energy landscape with software-defined electricity, a game-changing approach to modern power management. With decades of experience in energy optimization, Anatoli is tackling one of the most pressing challenges of our time: the outdated power systems that strain industries, hinder renewable integration, and limit infrastructure growth. Whew. Don't worry, guys. It sounds a little more technical than it really is. We're going to get into it in the show. At the core of Anatoli's vision is SDE, a revolutionary technology delivering real-time optimization of the power systems at a microsecond level. By addressing critical issues such as voltage shortages, harmonics, phase imbalances, and power factor corrections, SDE doesn't just patch the problems, it redefines the standard for efficiency and resilience. With a 10x smaller footprint and 98% end-to-end efficiency, SDE is setting the benchmark for the future of electricity. Anatoli's groundbreaking solutions are already making waves, from saving industrial facilities millions of dollars annually to enabling the widespread adoption of renewable energy, EV infrastructure, and microgrids. His mission is to modernize the global power system, creating a more sustainable, resilient, and smart energy future that meets the demands of today's world and beyond. So with that, welcome to the show, Anatoli Oleynik. Anatoli, I'm going to be honest, I'm a little intimidated about this show. This is probably the most technical show we've done, but we're super happy to have you on the show. Thanks for being here. All right.
Thanks for having me, yeah.
So Anatoli and I are in a manufacturer's resource group. So it's a collection of experts that do all things manufacturing consulting wise. We do optimization, we do leadership, we do electricity, we do machines, we just do everything. And Anatoli is an electricity genius. Anatoli, how long have you been doing this?
So I've been working at 3DFS, pioneering this concept of software-defined electricity since 2010. So it's easy to count.
2010, easy to count, right on the numbers. Yeah, 14 years. 15 years now, I guess. So this is what's cool. I knew that this was going to be a technical subject, but it's a really important subject. There's a lot of stuff in the news today about green energy. Like that's the big rage: renewable energy, green energy, all these things. But you're actually talking about something much more important, and that is clean power, not green power. Can you help me understand that?
That's right. And clean power has to deal with power quality. So we were having a discussion before the show about athletes, but you could think of clean power just like the air we breathe, the water we drink, and the food that we eat. The better quality it is, the better we work. And that's how electricity works, and power quality within electricity. The better the quality, the better the appliances work, and also how long they last. So one example is a fridge. Here in the US, a fridge will last, well, some of them will outlast you, but definitely around the
older fridges for sure. Yeah.
And you take that same fridge and you put it into power networks around the world, like in Africa or in India, in rural parts, and you're lucky to get a year out of it. And the difference, it's the same fridge. It's roughly the same place in the world, or at least climate wise, but the difference is the quality of electricity. So looking at it as an opportunity rather than a burden is,
Yeah. So maybe another way to look at that, and correct me if I'm wrong here, is if you have a 16-year-old and you're teaching them to drive your car, and they're just slamming on the gas and slamming on the clutch and slamming on the brake, and they're not giving you consistent, smooth transitions in power, that's going to be much worse on the engine than if they know how to feather it like a more experienced person would.
Drew, that is actually an excellent example, and that's really good. I might have to use it, but I haven't, so I could relate.
Yeah, yeah,
yeah.
I have a 17-year-old now, and I got her a car, but it's a standard, and so now I have a standard car, and she has my old car. But we spent an afternoon on a hill, leaving skid marks at different spots on the hill as she tried to learn that feathering strategy. But yeah, in power, in that you go to a third world country, or if in the military, if you're doing a forward operating base, or if you're working in like on an aircraft or on a tank, the amount that the generator is putting in and the amount that stuff is being pulled off can be way worse than it is here in America. In America, it always just works. You turn on the light and it works. But the truth of the matter is, to electronics, especially to motors and more sensitive electronics, those fluctuations really wreak havoc.
Yeah, and it's one of these things that we try to relate electricity to water, but they are similar, but they're different in the sense that as soon as you flip that switch, that instance, nearly at the speed of light, electricity has to be there to power on that light bulb. And with water, you have some pressures, there's some lag in the system. So it's not
There's a physical delay. Yeah, totally.
a delay, and everything from measurement and how you manage it is delayed. It's not real time. With electricity, and just like in driving, you have to be looking in real time. You can't and this is an interesting approach. So the traditional way that we've been looking and working with electricity is looking at it in RMS, so in averages and in 5-second intervals. So just imagine every 5 seconds I unblindfolded you and expect you to drive the car. So that's what's happening. And this is fundamentally how electricity is managed and controlled. It's based on averages and second data. So the decisions are not always correct because they're either over or under what needs to be done. So it's oversteering or understeering, hitting the gas too hard, not enough, whatever is happening. It doesn't happen fast enough. And that's why we have a lot of inefficiencies within our grid. So our grid has been around. So most of what we see in the grid, 70% of it dates back to the 1960s.
Yeah. Well, we were talking about this before the show, and I think that we live in a world of super thin iPhones, right? Like these like razor thin little iPhones, and that's because of the manufacturing capabilities that we have. But the truth of the matter is, a lot of our technology, like the basics of our technology, were from the 60s or even earlier. The difference is our phones, we pay thousands of dollars to keep these things razor sharp and exciting, but it's super expensive to upgrade the power grid. And so the power grid is essentially, like you said, it's essentially a 1960s device.
Yeah, well, and the way we've used the grid has changed from the 1960s, where in 1960s it was motors that would run all day, lights that you turn on at night and run at a certain schedules, incandescent lights. And now it's LED light bulbs, it's variable frequency drive motors, AC DC inverters, and fundamentally different loads and characteristics of how they're used. So and if you think about it, a lot of the infrastructure hasn't really advanced as far as really where we are with an iPhone. One example I've heard is, if Alexander Graham Bell comes back and he says, you give him an iPhone, he'd probably be pretty impressed and amazed. But if Nikola Tesla and Thomas Edison started walking around today's grid, they could name most of the components. That's a capacitor bank. That's a filter. That's a transformer. Oh, that's an insulator. They remain the same ever since their times. There's been certainly many improvements in material science and in making those things much more effectively, advancements on measurement. But from what I see in the field that we're been moving forward in the last 10 years, it's still got a ways to go. We still have a ways to catch up on the electrical infrastructure as we did in cell phones and many other innovative areas.
Yeah, no, it makes total sense. It's a little bit on the one side, it's kind of impressive that we're still using that older technology. It's kind of like still using Frankenstein technology, right? Like we still have those big like I don't know what the disconnects, the giant disconnects.
Oh yeah,
they're just smaller. So to kind of maybe bring this into a touchable spot for the audience here, we've all seen those they're gray or they're green electrical boxes in a subdivision, like, and they kind of whir, and we're all familiar with walking around a factory, and we know that there's like, oh, that's the electrical spot. Like there's kind of coils and there's a bunch of wires that go in here and there, and there's these huge metal cabinets. So talk to me, what's going on in those cabinets, and how do you do that because you do it 10x smaller footprint than what's currently going on. So before we get into your magic, what's really going on in those boxes?
Well, you bring up a good point, and going in, zooming out, the grid is usually, the power wires and the solar panels, what we see. But we don't see is what's actually going on in our own infrastructure. Because in a sense, it's most of the problems actually, and this is industrial and commercial facilities originate from inside of the facility. So you're not really necessarily saying, oh, the power coming outside is bad. It's actually what is the power generated inside? And inside you have transformers, you have various loads configured in various ways, and they all perform different things and they interact with each other. One key thing is with multiple variable frequency drives, they start interacting with each other. And if you turn them all at the same time, they create problems. They, and
So,
getting, yeah.
so I mean, this is a super simplified version of this. I have 3 teenagers and a 10-year-old and myself and my wife, and we all have to get up ready in the morning. And so it's a race to see who gets in the shower first because the shower is cold by the end of it. Now that's not frequency interactions, but what I'm saying there is the load on the hot water heater drains the hot water heater. Now, if given enough time, if I took a shower and we took a break and they took a shower and we took a break and they took a shower, we could all have hot water. But forcing that load at the same moment steals all my hot water. And sometimes it fluctuates, right? You're in there and you can tell when somebody else gets in their shower because it dips a little bit in temperature. Is that a good description of multiple loads happening?
Yeah, that's a great description. And if you think about it, there's 3 of these sets of showers in industrial and commercial facilities. And those represented by 3 phases. So you draw power on those 3 phases. Now, you have things that draw on 2 phases, things that draw on all 3, things draw on 1 phase, and you can't really control where they are when you turn them on. So what's happening in industrial facilities, you have this constant imbalance of how loaded each phase is.
So this reminds me of I used to prank my older brother, and I would either crimp the hose when we were outside, like running the sprinkler, or I would step on it. So like the job was I was trying to cause a pause for him to look at it like a cartoon, and then I would try to pick my foot up and spray him in the face, right? So you essentially have 3 hoses that are being stepped on or crimped at different times, and if it works out wrong, nobody's getting any power, or people are getting sprayed in the face, and that's a major imbalance in the power that you're generating on site.
Well, and actually, you kind of go down a more serious topic. So the unbalance in current creates neutral line current, and that is the number 1 cause of electrocutions and fires. So the more unbalanced the loads are, I think it's 80% of the electrocutions and fires are correlated to somewhere of either overloading the neutral wire or having loose connections in it, creating the arcs. So it's a little bit more of a serious consequence, but the concept is right on. It's because you can never balance the phases. You're going to use things how you're going to use them to operate your business or to use your electricity. And one of the things that we do is automatically balance those phases. So no matter what the load is, it's evenly distributed, which is a very critical component to how you have to work with electricity in real time, rather than the method that is recommended now is, okay, if you have this unbalance, go and plug stuff and plug them into different phases, run new wires, put those wires into those loads and plug them into that load. So that way you should have somebody watching, how disbalanced your phases are and rebalancing your panels, which it sounds good, but practicality, it
sounds like an electronic, like an old telephone switchboard. Is we're just guessing and checking. That doesn't sound like a great way to run a business at all.
Yeah, well, and that's how fundamentally a lot of infrastructure runs. It's we're still on the switching telephone networks. Some of it's done with software, some of it's done with automation, but there's an enormous complexity to it. So where you can't have one of these stations at you can't have somebody sitting at your breaker panel remanaging your loads, so that way you have the most effective and safe operating environment, electrically speaking.
Yeah. So I think the reason that most folks that are like in an office environment don't think about this is all that magic happens in a black box or in a gray box, as it were, outside in the shed. And I think that, maybe you rerun the clock 20 years. And frankly, we had enough energy. We had enough power flowing through the grid that we could just keep all the hoses full pressure. And if somebody was squeezing this one or somebody was squeezing that one, yeah, we can deal with it because there was enough pressure on the grid. But that's not really necessarily the case going forward, right? And this is not just an industrial problem. This is a residential problem as much as it is an industrial problem.
Oh, absolutely. And tell me if I'm going a little too far on the geek end, but what it really relates to, another point, is the type of energy generation that we have now versus when we did back in the 60s.
Okay.
Fundamentally, back in the 60s and still now, a lot of our energy generation is large turning turbines
Yeah.
that basically boil some water some way and turn a giant steam turbine that turns it and makes electricity. Now, what that turbine has is a lot of inertia, to where that massive amount of weight that's just rotating, it counteracts any issues that come across the grid or any disturbances, unbalances, because you're dealing with a mass that is, I mean, just imagine, all
Yeah.
of those hydroelectric, nuclear, coal-fired plants and the massive amount of rotating weight and how hard it is to stop it. And now things are a little bit different with solar. There's no rotating mass. It's an inverter that pushes the power. So all of the issues come down to, well, we don't have the resiliency that we once did from the power perspective, and we need more energy. So
what you're saying is that the old way we used to generate power was constant. So we just kind of like a water tower. Like there was just constant water pressure. We would use a little bit, but the water pressure was always there and it was always constant. But the new forms of energy we're talking about wildly vary in how much they push out. So it's kind of like if you had I don't know, maybe you had a kid with a bunch of super soakers at the top of the water tower, sometimes pouring it in and sometimes not pouring it in. And that's only going to get worse as we move to more renewable sources.
Yeah, well, and renewable sources are not bad, but that's an opportunity for more efficiency, because one area that you're not looking at is putting in, well, number one, storage. It's an area that people are looking into, but then the secondary part becomes, okay, you're still using an inverter, and many different inverters inside of a system, they create power quality issues that have to be cleaned up by transformers, the loads themselves, or spinning inertia. And there's a lot more details to this, but that's the 10,000 foot forest view of.
Well, maybe this will help. If we have a table full of china, so we have sensitive electronics. If you have a table full of china and the table is being powered by a bunch of double Dutch jump ropes, like my daughter who's 10, she's got a jump rope and she's spinning this jump rope. Somehow magically, because she's spinning this jump rope, it gives power to the table. But if you had 20 of her around the table and they're not synced up with each other and they're just spinning jump ropes and some people are doing this and some people are doing this, then the power that china table is going to rattle itself to death. Is that a fair analogy?
Yeah, that's a fair analogy. So, stability is paramount in the more power we deploy, because now the demands are massive. Data centers are hogging up. They're the new super consumer. And now they're discussing becoming their own utilities in some ways, which leads you to, why not do it efficiently? Why not update and become better than the modern or the pathway that we went? Because there's an incentive in production. There's an incentive of, at some point it gets down to how much electricity to generate, how much is the cost, and how many flops of compute power I can create, or whatever the variable is for the product that you're trying to create. In the mining industry, it's how much coal and how much does power quality cost. There's a very well calculated cost of about $2 million a facility, plus or minus, and that's. Some figures integrate the actual cost of missed opportunity of how much coal you could have extracted out of a mine, and how much you just spend doing it. So both things play a factor into efficiency and resiliency.
So what you're saying here is that there's a cost to generate electricity.
Yes.
Right. And it's not just the cost of, like, we all think of a generator. You might have a generator at your house in case it snows, like it's been cold lately. So okay, we have this generator, and I got 5 gallons of diesel or whatever. Okay, I can run my generator, but that's not really. There's an efficiency loss when I burn that generator, right? There's a cost to create the generator. So I think that because we all live in homes that are heated more or less reliably, we don't appreciate the industrial problem, which is about to become our problem because of EV vehicles. I don't think we'll talk about that here in a second. But on an industrial scale, if you're running a Toyota plant or a Hitachi plant or something like that, you're consuming more energy than the grid really can produce for you. And so let's say I have 2 generators right here. Generator 1, and actually let's say I have 3. So we have 3 phases, right? We have 3 generators, and they're producing electricity for me. There is a loss in that generation that I could recoup. So it's not just, hey, the cleaning up the power is not just about like making the vibrations better somehow magically in an electrical sense. There's actually an efficiency gain where you can get more useful power out of the system, right?
Oh yeah. Well, how you use the power, if the quality of the power is stabilized, then you're using that power more effectively. And there's a correlation to both how much fuel you're putting in there, how much more efficient the appliances and all the infrastructure runs, and how often you have to replace it or maintain it. You're going back to vibrations, but that is one area that you can actually see inefficiency. Why do transformers hum? It's inefficiency. And getting into inefficiency problems, the inefficiency of transformers, I would argue, is idle load. So when they're not doing anything. So in the middle of the night when there's no draw, that's where you have the greatest amount of inefficiency, because they're made to run at 80%. When they're below that, their efficiency is wildly worse.
I think that's a fantastic idea. The fact that you can literally hear wasting money when you hear the hum of the generator. That hum is energy, because it's becoming sound energy. That hum is literally energy that you're not being able to put to work. That's a super fantastic idea.
That's one way. And then if you think about it, the heat on motors, if you touch a motor, the heat, why does it's a rotating transformer, why does it get hot? Well, inefficiencies. You look at electrical wires, why are they hot? Inefficiencies. Some of it may be they're carrying too much current, but harmonics play a role into this one. The more harmonics you have in a system, and harmonics are probably the easiest way to understand them is sound quality. So back in my day, we had cassette tapes, and they the sound quality wasn't the best, and you could tell that there's a better sound quality when you had a CD. So that's basically the noise that goes to the power lines. The more noise you have, the further the current will travel on the outside of the wire, which is getting on the geekier side. But the more current it generates, the hotter the wire is. So that's more inefficiencies. But you're thinking that, well, this inverter or this appliance that produces light is more efficient at producing light. Yes, it is, but it may not be as efficient throughout the whole network. So you got to look at not only the output of an appliance, but also the input of the appliance back to the grid or back to the local grid that every facility has.
So is that kind of like if we're at a big long buffet and I'm passing a bucket of ice cream down, I'm going to eat a certain amount of ice cream, and then I'm going to pass the ice cream to the next guy. But depending on how much I take right now determines what the next guy gets. And I'm not taking the same amount all the time. Is that?
Okay, so close. The way I would say it, I would compare it to capacitor. So when your AC breaks, probably the first thing that fails on it is the capacitor, and the HVAC technician has to go in and put one in.
I did that. I did that in October.
Okay, so you know what it is. So why do we use capacitors? And capacitors, they essentially shift power factor, which is a broad term, and there's so many really fascinating details in what power factor is, and really understanding it. But we're looking at the surface layer, the very simple analogy. If you think about power factor, it's basically reactive power is the foam on your beer. So when you you pay for a beer, and how much foam you have is the offset power factor.
Ah,
And so what happens is if you're feeding this your air conditioning system with whatever foam, the capacitor basically supplements some of that foam with real electricity, but it has a cost. It creates harmonics. It's only 50% efficient, and it's rated at a specific load, the sort of either your startup capacitor for starting up the air conditioning or for running it, which is a constant load. But if you zoom in a little bit, well, there's variations within the operation of that HVAC system. Differences when your filters are clogged, it's got to pull harder. When there's 100 different variations of why it's never going to be pulling the rated current that the capacitor is designed for, and the capacitor wears out. So it's always missing the point. And essentially, what we're doing with power factor is we're measuring it at a very high resolution, building a model, and then constantly shifting it to coincide exactly where the demand is. So it's always matching. And that's a good comparison of one component of it, but that's power factor.
gotcha. And now you're doing this through so the way that we do that currently is it's a series of circuits, a series of of sensors, and then an algorithm, and then a switch, right? We have power comes in, we decide what we need to do with it, we do a processing cycle, and this takes time.
Yes.
Now, to us as humans, it's super fast, but there is a faster way to do it rather than just through programming, right? And that is a cool little system called an analog computer that I think that you are using. I'm not going to ask you to go into there, but I think the magic here is that it's kind of like setting up a pulley system that just naturally works itself. It doesn't take a processor; it just works. Is that right?
It is, and that's what gets into fascinating of what we're doing. So the traditional ways of doing it, and we can, our capacitors, multiple banks of capacitors that turn on and off at various times, or filters that turn the inefficiencies into local heat. They're massive. They require air conditioning. They require maintenance, and the bigger they get, the more management and oversight you need over them. What we're doing is essentially a completely different way. We're using real-time measurements. We're taking those measurements and building a model of what the electricity is doing at that time. And think of it as it's not AI, it's analog computing is a really good example. And I would love to have a conversation about this topic, but it's going to be a long discussion.
It's a cool topic.
It really is.
Analog computers are super cool. Actually, so the easiest analog computer is a slide rule. I think everybody in the audience has some working knowledge that somehow magically, because of the measurements on two rulers that you slide against each other, you can get an answer nearly instantaneously. That is a very, very, very basic analog computer. As it turns out, you can do a lot of amazing things, and I'll probably link that Veritasium video in the comments here. But analog computers are super exciting, and it's a whole branch of computing that we've gone away with. But they're more efficient once you design them to do a specific task.
Exactly. So call it an expert system, analog computer. There's different ways to describe it. But yes, it's essentially a whole operating system for just electricity. So modeling, understanding electricity, and dynamically in real time with solid state electronics, balancing that electricity to perform its best at whatever the load is, or optimize all the parameters of that electricity for the loads and generation and throughout the whole network.
So by using this system, you can replace those big gray boxes that are full of resistors and capacitors and switches and computing power, either in your local subdivision or at a large factory, right?
Well, not
necessarily have to replace them.
Not replace them. No, it goes in parallel to. If there's existing capacitors or filters, they'll just last longer and they'll be more effective at what they do. What this does is it fixes the main problems and the subtle problems that traditional systems just don't have the speed or competency to respond to at that level. So overall, it's an additive solution that either by itself or together with traditional approaches, it makes the efficiency and reliability of the electrical network much greater.
That's super exciting. So you have essentially a bolt-on system
Yep.
that it can increase the efficiency of the power nodes. We get more power for the same power we currently have, and it will make all of my systems last longer. That's a return on investment that I think you can take to the bank. That makes a lot of sense.
It is, and that's one of the ways that we're working with customers is actually better understanding their end product, whatever that may be, whether it's coal, data, or you pick a category, and that could be considered the end product of an enterprise, and showing how optimized electricity makes an impact on the so more product at less cost. That's what it comes down to. And we believe with this formula, we have an impact and our ROI that makes sense. That's practical. That's not a go buy all new infrastructure and see what happens. It's let's put in this solution at a price that is the savings and the benefits it provides offsets its costs.
Yeah, that makes total sense. Okay, so if I'm listening to the show right now and I am a general manager at a plant, maybe I'm a VP, maybe I'm a CEO. It seems like maybe it's a little bit over a CEO's head, but if I'm somebody that is in charge of making sure that this plant is the most efficient that it can be, what is a good way to reach out to you and connect and find out more? Practically, how can I put this at my factory or at least try it out?
Yeah, well, I mean, most practical way is start looking at your electrical network, do an assessment for measure your power quality, see and understand what is going on. Look at the numbers, look at the data, and let that guide your decisions. And then what we do is once that infrastructure is in place to measure and quantify what is going on, we go in and we install a pilot to basically measure the difference, measure the delta. What do we bring to the table? And quantify what we do and how it impacts the operations in a way that makes sense. But first is get a better understanding. We certainly have some materials, white papers, and information on different industries, how they're impacted on our website.
Yeah, and so that's 3DFS, so 3 Delta Frank Sierra.com, 3DFS.com, and it has all the all the literature that they're going to need. It has the case studies there, has a description of the products, it has a way to get a hold of you. Is there anything else that they should they find you on LinkedIn? Are you on LinkedIn, or how can they get a hold of you personally?
I am. LinkedIn is probably the best way. And
well, cool. Well, it's showing on LinkedIn right now. So if you're watching on LinkedIn, reach out to Anatoli Oleynik and ask him to come out and take a look at what your power generation needs are. Anatoli, I think we're kind of running short on time here. So they know how to get a hold of you. When they work with you, you're going to come out, you're going to help them work through their needs, propose a pilot project, and then it's a bolt-on solution, right? So they can actually try this out without having a major capital expenditure up front. Is that correct?
Yeah, so it connects in parallel, so it installs much like any other appliance. And that's also the fail-safe. So for whatever reason, if somebody drives a forklift through our controller, you're just going to go back to the way that power was. So it's a very low risk way how to find out what's the difference, how to make a difference, and have a quantifiable result.
That's exciting. So that's factories, large factories, medium-sized factories would also benefit from it.
Yeah, medium-sized factories, data centers. Really, we have not found an application where it does not make sense. Obviously, operations that are running 24/7 and then have dynamic load profiles are going to be the best fit for what we do. And especially automation, robotics, the more of that, the more value we bring to the table.
So does it make sense to do this just on site, or does this make sense to do maybe at like a power station at a utility, or like I don't know, what do you call the power stations that are like, they're just like halfway between a factory and the utility? I drive by, there's one by my father-in-law's house. A substation. There we go. Yeah. So does it make sense to do these at a substation?
So right now we're primarily on the low voltage side. When you consider low, medium, and high voltage, we are getting to the higher voltages. We have projects. We have interesting announcements to make on how we partner with other manufacturers to integrate this as part of their infrastructure. But overall, the benefits really behind the meter to the user, and the other part is microgrids. That's where the other interesting aspect of what we do comes into play with having microgrids that are have multiple generation sources that are disconnected from the primary grid. This is where resiliency, stability are really important. And that's where we have a lot of interesting topics to discuss.
Oh, that's cool. Actually, so some of my work over the summer brought me in touch with some microgrids. I know that factories, because of the power grid that we have, like the more global power grid, it's kind of 1960s technology. It's aging. It doesn't, like you said, we're measuring in 5-second intervals, not microseconds, which is where power really happens at. People are looking at cogeneration. They're looking at how do I put micro generators on my facility to get the energy that I'm not getting from the grid itself. So that's a great application. We are running up against time. So, Anatoli, I'm going to give you the last kind of 30 seconds to close out with anything you want. Listen, reach out to Anatoli. Tell him you saw him on the Drew Sutton Leadership Show. Ask him about the difference between clean power, not green power, and how you're going to be able to save 10x the footprint and 98% efficiencies by working with his software-defined electricity. All right, Anatoli, over to you.
Oh, that's it. Thank you for having me on the show. And
yeah, thanks for it. It's a tough concept, like to work on in this kind of a non-technical environment, but I think you have a great handle on it. I appreciate you being on the show.
Yeah, thank you.
Yeah, and so with that, go find Anatoli, find him on LinkedIn, find him on his website, go read those case studies, mention it to your vice president or your director friends, your general manager friends. This is a great way for them to protect their investments and stay viable as we move into this new green and electrical vehicle power grid world. So with that, we are out.